briefing. We've had several briefings on various aspects of the Constellation project as a whole. Our subgroups have had a near infinite group of briefings. Today, the group as a whole is going to get another segment of the Constellation project update. And we have scheduled an hour for this, and I want to be sure you get at least that hour. So don't be concerned that we're a little behind. We'll find a way to make up, we'll take our reserve out of someone else.
All right, thank you, sir. I'm Jeff Hanley. I'm the program manager for Constellation. I'm happy to be back here in Huntsville. This team here in Huntsville that is managing the Ares 1 project and the center that supports the project and the community that supports the center has really embraced Constellation and has really gotten it moving here these past 4 years, and some of that we will put on display here today. I'm gratified by the words that and the display of understanding that Bo and Gary both portrayed. I think the assessment that we saw here this morning was fair. As program manager, I'm paid to be a pessimistic optimist or an optimistic pessimist. I'm not sure which. I of course have a different view based on the tools and landscape that I see, a different assessment, and we can share that with the panel as to our executability. Not quite as pessimistic as the aerospace study, but in the range, particularly with schedule, the outcome of schedule, looking at schedule risk, we found to be a little bit like hurricane forecasting and trying to forecast which model to believe as to where landfall is going to occur. There's a range of models we use to assess the outcome of the program, both from a cost and schedule perspective. Those are informing our decisions, and we've shared those results with our independent assessors as we've gone through this process, and we're happy to provide those assessments as well. But I think the assessment that you've seen here this morning stands on its own merits. There's a famous prayer that I've come to really appreciate the past 4 years of the Serenity Prayer that probably many of you know, the serenity to accept the things I can't change the things I can, and the wisdom to know the difference. And that's really been the emphasis of the last 4 years in learning for this team, for myself, and I think what you'll see here today is the active management of the program here in the Ares portfolio, the active management to address many of the challenges that we face in bringing Ares 1 and Ares 5 to fruition. So let me hand it then to Steve Cook, the project manager here at the Marshall Space Flight Center for Project Ares.
Thank you, Jeff, and thanks to the panel for the opportunity this morning to speak before you for the second time. When you were here the last time in Huntsville back at the end of June, enjoyed the opportunity for the dialogue and to show you the progress that we're making around the center on our hardware, and it's good to be here again. And this morning we're going to give, actually we're split over the morning and the afternoon, so the way we've set this up, Mr. Chairman, with your agreement, is we've got an hour that we will go through part of the Ares programs. We have an hour then after lunch where we'll finish up the Ares story and also talk some of the other parts of the Constellation program. And we'll allow, I think probably the best way to do it is to have Q&A after each one of those sections. Otherwise it gets late into the afternoon. Is that acceptable, sir?
That sounds perfect. Thank you.
Great. Okay. Next chart, please. So we've been off and running for 4 years. In fact, we had the task assigned to us 4 years ago almost exactly this week as we were completing the Exploration Systems Architecture Study. And by the way, 4 years into this, one of the things that I know is I look for trends. One of the trends that I see is when I see five Macs and one PC, and I know that the Ares project is mostly Mac, I feel good about that. So I know we're not supposed to read into what you're doing, but I think that's one thing we can do. It's really been both a blessing and an honor to be a part of this team. We've made tremendous progress from literally a paper concept study 4 years ago to now we're almost a year pencils down on our preliminary design review, well heading to CDR. Aries is really a family. It was designed to be a family. 1 and 5 go together. That was a big part of the approach that we laid in early. It is shuttle derived as well as parts of the ELV system, and of course the heritage from the Saturn program. And that's a good part of why we ended up with the system we ended up with. We were trying to have a good transition from the shuttle program, basing our lessons learned over the last 50 years and bringing them into the systems we're putting together today. With the Aries 1 and 5, we're going to have 60% greater capacity to the moon than we had with the Saturn program, and a substantially lower cost. In fact, approximately, if you look at the Saturn cost per pound to orbit compared to where we're at on Aries 5, because we have designed in, or we are designing in today for sustainability, we believe that we'll be on the order of 60% cheaper than we could do in the Apollo program. Again, difference in focus. The focus here is on sustainability, having that margin to do a significant number of programs out into the future. I think we've had a computer problem, so I'll just kind of keep talking, and when the computer catches up, we'll get there with that. Let me talk a little bit about as well the benefits that we've got today with the Aries approach with Aries 1 and Aries 5. Aries 1 is really the stepping ground to Aries 5. We will learn significantly from the booster, from the first stage in flight, gathering critical flight data that will give us greater confidence when we move to the Aries 5. The same applies to the upper stage engine, the J2X, which we use on both vehicles. That's a significant advantage. Again, I see Aries 1X, our test flight, as a crawl, Aries 1 as a walk, and Aries 5 as a run. When we haven't done something like this in our industry in over 3 decades, I think it's important that we take it in a stepwise approach. And so we and our industry partners are learning as we put this whole program together as we are successful. If we look at Aries 1 itself, when we look at the benefits of the Aries 1 and what it brings, from a top-down perspective, it is important to look at some of the characteristics that we believe that we get out of this approach. Number one, top-down, is that commonality that I've already talked about between Aries 1 and 5. So you can crawl before you walk, before you run. From a bottoms-up perspective, though, what we get is, because we're using a first-stage system that is the most reliable propulsion system today that is flying, Soyuz is just slightly behind it, a system derived from the solid rocket booster on the space shuttle. We believe that will give us a much greater chance of having both a reliable and a safe system. And Dr. Joe Fagola will follow me and walk you through our safety story and our safety approach and how we have designed in from day one into the overall Aries family. We believe that based on our analysis that we'll get at least a factor of 10 better than the space shuttle today and a factor of 2 better than other systems. Why don't you go forward, please, if it'll work. All right, next chart, please. Next chart. Thank you. 30 off, if we look at risk reduction, Aries 1 allows us to, much like the Saturn 1B, flesh out the issues on the Orion system, both in ascent and then, because we get it to orbit, orbital environment and reentry, on the smaller vehicle, on the cheaper vehicle up front. It is that stepping stone from one point to the other. It also allows us to transition our shuttle workforce from one program to the next. When we talk about heritage and we talk about heritage systems, we tend to focus on the hardware. I think what's even more important to talk about, and Robert hit on this morning, it's more important to look at the workforce and the capabilities that we are driving. We are taking the engineering teams from the Space Shuttle solid rocket motor and applying them to the first stage. We're taking expertise down at Michoud, where we build the external tank today, and applying that to the upper stage. We're taking expertise that Pratt & Whitney Rocketdyne has gained up through work on the Space Shuttle main engine and the RS-68 engine and applying it to the J2X. And so this is really an ability for us to transition appropriately from one system to the other. And in the end, having a government system to LEO that is a stepping stone to a system for beyond LEO gives us dependable U.S. human access to space. Now that's Aries 1. Let's talk a little bit about Aries 5. Well, Aries 5 is really a game changer in terms of its capabilities. It will give us 7 times approximately the lift capacity of anything else that we fly today, with significantly larger payload volume, looking at on the order of 10 meters, almost 10 by 10 meters of usable space in the volume. And if you talk to the user community, they're actually more interested, outside of human exploration, they're more interested in the volume than in the mass that we're going to give. It allows us to look at a wide range of diverse missions. The National Academies last fall published a report on the use of constellation, and they spent an awful lot of time on the Ares 5 and how that could be a game changer in terms of scientific missions, whether they're large aperture space telescopes, and you'll see an example of that this afternoon, or flagship outer planetary missions in much, much lower time. It really is an enabler for looking at missions, being able to, for example, image another planet, having the capability to do that, and that kind of volume and mass allows us to get there. And really the U.S. is in a unique position to build a heavy lift system of this class. We've got our legacy production and operations capacity from both the Space Shuttle, from the EELV programs that we bring into the system, and that includes the infrastructure you'll see tomorrow down at the Kennedy Space Center, the vehicle assembly building, the crawlers, the pads, all of that. Frankly, if that national capability is lost, it's going to be very hard, and we may never recover the ability to do something like this. And I think when you look at where other countries are going, they don't talk about something in this class because, frankly, they don't have the ability to build off of something like we have today. And so I think that puts us in a very unique position and is important to consider as we look at our launch system capability. Next chart, please. And if we plot here, then the various missions that the various architectures, A through E, that the panel has been looking at, both lunar surface missions, go to a lot of different destination missions, go to near-Earth objects, and then eventually on to Mars. You see those plotted, A through E. And you see down below where the Ares 1, Saturn V, and the 1+5 stack up against that. And what you see is that the Ares 1+5 gives us a very robust capability to address all of the missions that the panel is off assessing today, and Dr. Crawley's team has been looking at. In fact, I think he's got a slightly different version of this chart that he'll show tomorrow in terms of the various launch vehicle architectures. The other thing that you can pull off of this, it's very interesting and instructive, is about 50 tons to translunar injection is really a gateway point for enabling a wider array of missions, whether that be lunar surface, NEOs, or Mars assembly missions down the road. That is a real key driving point. And so what that tells you is, the folks building the Saturn, we have that legacy here in this town, and if you go upstairs and you see it laying there, they had it about right in terms of what it takes to have that sustainable approach for exploration, because we're trying to enable several destinations. Next chart. So let's talk a little bit about Ares 1. We'll spend most of our time today and tomorrow talking, or today and this afternoon, talking Ares 1, and then we will also give you an overview of Ares 5 and where that stands. Now, let me start off by saying our acquisition model here is somewhat different. And General Lyles, you asked the question yesterday of Mark Geyer about this new model, and I think we had an opportunity to chat when you were here in Huntsville about this. So, and the model is really the Saturn model, where NASA is serving as the prime integrator for the entire launch vehicle. The government, is the prime. We have key contractor partners, obviously, in this. The first stage is being developed by ATK Launch Systems, the upper stage engine by Pratt & Whitney Rocketdyne. You see the relative current contract values. That is for DDT&E only. And then we have the instrument unit and the upper stage, where we have another unique model, again very similar to parts of the Saturn, where NASA is leading the design, and we brought on Boeing about 6 months prior to PDR in order to help us build a more producible design and then to produce that. And as we are moving now through the design cycle, Boeing will take on larger and larger chunks of that work, because the sustaining engineering, by the time we get to the design certification review, will be the responsibility of Boeing. So we're in that handoff stage. As we move from PDR to CDR, Boeing takes more and more responsibility. Now, the reasons we chose this model early on was, first off, this is a multi-generational program, and we haven't done something like this in a long period of time. And it's going to be here for a long period of time. I think there's some lessons learned from the Space Shuttle in terms of intellectual property and where the intellect lies for solving problems 20 and 30 years into a project's life. We applied, when we started this program, there were some pretty critical reviews coming out on space acquisition in general. One of my favorites is Mr. Tom Young's report on space acquisition that came out in 2004, and a couple of key recommendations there was that the government was losing some fundamental internal systems engineering capability, and hand in hand with that is our is our capability to manage large projects. And so this was a means to start ensuring that we take the core capability that we have in the government and rebuild that capability. It's not the intent that we would pursue this model to this degree once we move into Ares 5. In fact, we know that we can't, because we frankly are at capacity in working on Ares 1 with this model. But now we've got a lot of smarter buyers within the project management realm, safety and mission assurance, and engineering that have gotten their hands dirty. And I think, as you saw on the tour here the last time, there's a lot of folks getting their hands dirty every day. And that's going to make us better when we go build the largest launch system ever developed, the Ares 5, and put that into place. So we believe that in this phase, this is an appropriate transition into a longer-term model where the government still has much more active role, but it won't be to this extreme as we move into Ares 5, but we do believe this marries the best of industry skills and NASA skills for the Ares 1. Next chart. Here's the team we've got today. We've got over 4,000 folks nationwide, over 324 organizations across 38 states. It takes a nation to put together a system like this, and we've got small businesses ranging from up in Oregon to Minnesota down to South Alabama that are helping to put this project together and make it successful. This is really about the people, and so we've gone from basically employee 1 4 years ago this week to about 4,000 folks on board, which you would expect as we're heading into the critical design review phase. Next chart. Here's our schedule. This is just a top-level summary view. You can see the blue line there in the middle. Kind of shows a demarcation of what's been completed over the last 4 years. We've completed over 200 design reviews to date, ranging from components through subsystem elements and full-up systems. Of course, we've completed the preliminary design review for the stack itself and all of its associated elements, and we actually completed last November the critical design review for the upper stage engine, the J2X, and now we're into manufacturing for the first development engine to put that system in place. We've got a lot of milestones, a lot of runway behind us. We're about a third of the way through the development from an overall dollar standpoint in terms of executing the project. And we've got some pretty key milestones up ahead, and you see it right there later on in about a month, on August the 25th. We've got development motor number 1 for the first stage, which is our first 5-segment motor firing that is set up for the Ares 1 and Ares 5. So that's our next really key milestone, followed by Halloween. We promise we hope to not make that a trick-or-treat. On Halloween to have Ares 1X flying, which is going to be a really key part of our strategy, because that's something else that's different, is since Apollo we hadn't had a development flight test where we could actually have engineers in a relatively short cycle from start to finish, just a little over 3 years, go through a full development cycle on a test rocket. One, the learning for that workforce has been enormous, and the lessons we've learned have been almost immediately transferred over into the mainline Ares 1 and Ares 5 projects. But we have over 900 pieces of data, 900 channels of information that we will get off of this system that will allow us to validate a lot of the design work we've already done to date. And we are doing it sufficiently ahead of critical design review that if we find some things that aren't working like we thought they were, and I know that will happen, that we can inform our design. And that's a critical part of the risk reduction path. And we'll talk about Ares 1X and what it does for us later on this afternoon. Next chart. The other thing that I think is important is that we have to earn our value every day in what we do. And so we've brought in rigorous earned value metric management throughout this project. This is our latest June-July report. You can see our CPIs and SPIs up there. I won't walk through those. By the way, those don't always look green. All right, that's where we're at today, and that's we use this tool to help us manage, to put focus on where we have problem areas as we go through the development of this project. I'm proud to say that our team won the NASA EVM Award of Excellence just a little over a month ago for the implementation of EVM on in-house projects. You know, our contractor partners in large part are very used to working EVM in developments. We had not done that on the government side, and so we're well into to working through that process. Next chart. I mentioned the people. We talk about hardware a lot. You're going to see a lot of progress on the hardware front as I bring up some of the key leadership for the Ares team, but it really comes down to the people. And so how do we ensure that we're getting a quality product? Well, we've met our milestones. So from that growth standpoint, we believe that we're meeting our norms. And you see up there on the screen, what are the norms that we live by? And the number one norm we live by is that the team members have got to have fun. This is a tough job. Hasn't been done in a long period of time. And frankly, if we're not enjoying what we're doing, putting this together, this once-in-a-lifetime opportunity, that we're really blessed to have, then we're not going to get the most out of the workforce to make it happen. So that the managers have to walk the walk and talk the talk. We've got to encourage openness and diversity in ideas. I think we have done that. Constant communication is important, whether that be, and by the way, in my mind, email is not a form of communication. It's get into the room, have a conversation, work things out. And frankly, we were given a pretty straightforward mission. Go get this rocket built and get it done as soon as we can. Some of the challenges in doing that is we're taking a culture that's largely an operational culture, had been, and technology culture, and honing overseers into producers. Now that's been a challenge, but it's been also a great opportunity, because when we started this project, if we look at the history of what had led up to this, throughout the 90s we were in a very much a stop-start mode. We probably had 2 or 3 year cycles, and direction would change and we'd head off down another path. We've got 4 years under our belts on this one, and I think the folks really want to fly this rocket and make it successful. And knowing that, we've got to do that confidently, but with humility, because the hardware is going to teach us a lot as we get into test and we put these things together. The other key aspect of this I think is very important, is that training all of our engineers and our managers to think as a systems engineer. You're not focused on just reviewing one discipline or one subsystem. What are the impacts across the board? And so how do we inculcate that into the culture has been a very critical aspect. In addition to, how can we do this leaner? All right, we brought lean thinking in and lean practices in over 2 years ago. We've had, well over 100, I'm sure, lean events across the project to really focus on value-added items, and where it doesn't make sense, let's push back on a requirement. Let's do that wherever we can to make this successful. It's all of this, plus the heritage we bring together, that will allow us to have a successful program in the end. Now, let me start turning it over to some of the folks, next chart, that are going to talk you through some more of the details. We'll come up after the morning session, and we'll all be available for questions. I want to first introduce Dr. Joe Fragola. Many of you know him. He will be walking through our safety story and the work that we have done to drive safety into the design. And then, again, we'll have a session at the end for questions. Joe?
Thank you, Steve. Mr. Chairman, members of the committee, members of the audience, I'd like to say what an honor and privilege it is to speak before you today, to tell you a story that I've been sort of passionate about for the last 40 years. A story that is directed at what Bo challenged us to talk about, which is developing something that's a lot better than what we had today. And in this case, a lot safer than what we have today. Now, this story didn't begin with ESAS, and it didn't begin with Ares 1. So I'd like to take you through that story. The story was enhanced. It started with a Challenger effort, a post-Challenger effort, and it was enhanced by the Columbia Accident Investigation Board, asking us that in the next build of a vehicle to replace the space shuttle, that we give overriding priority to crew safety. And the astronaut office at about the same time set a very challenging goal of a 1 in 1,000 loss of crew during ascent. And I think those two motivations were the motivations behind the work that eventually led to what you see today as Ares 1. Next slide, please. Going through the history a little bit, after the Challenger accident, we had the Rogers Commission report and the Slay report. That motivated people to concentrate on revisiting safety and try to understand in the shuttle vehicle how we could enhance the safety significantly. The crew office under Brian O'Connor investigated ways to escape from the shuttle system. Despite all the efforts that were done, we recognized that everything that we did was going to increase the mass of the shuttle and decrease the payload to the shuttle, so that for the ISS missions, the payload decrease was such that the number of missions that had to be flown to bring the payload to the station would be increased to the point where the overall integrated risk would actually go up rather than down by the number of missions increased. At about that time, there was the first integrated assessment of the shuttle risk done in 1995, and we began to realize that the shuttle, although it's a tremendously capable vehicle and reliable as a launch vehicle, had genuine problems because of the safety limitations of the vehicle. So that led to two efforts. One directed at the improvement of the launch vehicle itself and its reliability. So-called shuttle upgrades were considered and added to the vehicle. And then to consider alternatives to the shuttle as launch vehicles that included abort. The reason for that is very clear, that we saw with the shuttle, since escape was not possible without degrading the payload significantly, and the upgrades only added incremental to the safety enhancement of the shuttle, the next generation of vehicle, to meet the challenges of safety, would have to include some sort of abort capability. That led to the consideration of the so-called orbital spaceplane program, which at just about that time, the conclusion of that program, the Columbia accident occurred. The crew office issued the memo that I showed you, and the Columbia Accident Investigation Board issued their charge to the next generation of designers. The orbital spaceplane considered alternatives that were wing-bodied, lifting bodies, and capsules. We found that in the descent and landing phase of the mission, both the wing body and the lifting body had advantages from a safety perspective. But those advantages were overwhelmed by the disadvantages in the ability to sustain a loss of mission, a loss of vehicle accident in ascent, which led us to the capsule concept, which we felt was more robust. At that time, the search was for a launch vehicle to allow us to incorporate the more robust and what we thought safer concept of capsule. We investigated at that time the full spectrum of available launch vehicles and proposed launch vehicles. Safest by far were those launch vehicles that included a single core and a single engine. But the problem was the payload capability of the single core, single engine vehicles was incompatible with the size of the capsules we were talking about. So that left us with a dilemma. And the crew office came up with a possible solution to that dilemma. And that was to consider a safe, solid first stage as opposed to a liquid first stage. With the enhanced 2.5 million pounds of thrust, it might be possible to incorporate with the newly designed second stage a vehicle that would incorporate the safety features of an abort system and also allow us the payload capabilities. That led us to the beginning of the so-called ESAS report, where we again investigated the full spectrum of launch vehicles and saw quite quickly that the alternatives that allowed for payload enhancement required us to go beyond a single-core vehicle to a so-called heavy vehicle, which increased the complexity of the system, and you'll see in a moment the reliability was decreased. Next slide, please. This is my favorite slide. It's not a very elegant slide, but I come from the era of the slide rule, the nomograph, and the carpet plot. And this is my favorite from that standpoint. It explains very simply how one converts from launch vehicle reliability to crew safety. What it says is that the conditional probability given an abort condition is important in establishing the overall safety of the vehicle. What that means is, even if you had a shuttle with extremely high launch reliability, if it has no abort capability, there's no way to handle the conditional probability of failure given an abort requirement. It also suggests that for the full spectrum of existing launch vehicles at the time this was done, you would require an extremely high so-called abort effectiveness in order to reach the goal that was set by the astronaut office of 1 in 1,000. So that was our challenge. Our challenge was to enhance the abort effectiveness and yet maintain the reliability of the launcher. Now, a subtle fact that's in here that wasn't spoke of before, and something I'd like to challenge a bit of what Bo said, is that it indicates, this chart, that it's not only important that the launch vehicle be reliable, but what is also important is that it be robust in enabling abort capability given a failure. And I think I should repeat that. What I'm saying is, it's not only the probability of requiring an abort that's significant, it's the condition that that requires that abort that is also significant. And if the conditions requiring abort are benign, then the effectiveness of that abort is enhanced. If the conditions requiring that abort are not benign, then the abort effectiveness is degraded. And the things that led us to the alternatives we considered was not only the probability that there would be a failure in the first stage or the second stage of the vehicle, but what sort of condition did that abort situation impose upon the capsule and on its vulnerabilities. And I think that's something that hasn't really been said. And that leads to the challenge for what Bo just said. I believe it's true, in my own personal opinion, that launch vehicles to Earth orbit have gotten to the point where commercial people can take over. But it's another thing to talk about a crewed launcher. Because for a crewed launcher, one not only has to consider the reliability of the launch vehicle, but the effectiveness of the integrated launch escape system and the robustness of that escape system against the likely failures of the vehicle. That is not a trivial exercise. Having been a person who sat with the leader of the Chinese safety program and spoken to him by hours about their conversion of their launch mark to a human-rated vehicle, I can tell you that was no easy challenge for them. Next slide, please. What this chart also told us was that it was no longer sufficient to consider only the logical models, the logical probabilistic models in the design process. We had to also integrate at every step of the design phases the physical processes that gave us the conditions that imposed environments upon the crew escape process given an accident. So through the beginning with ESAS, we attempted to what I called sculpt the risk. Sculpt the risk by identifying using the probabilistic process from the top down to identify the likely scenarios, and then using physical simulation models to simulate the environment created by those likely scenarios to determine the abort effectiveness. We did this through SOR, through SDR, to PDR, and then through CDR by stepwise enhancing the accuracy and the faithfulness of both our logical models and our phenomenological models. Next slide, please. In cartoon fashion, we began to evaluate the individual alternatives. And you can see from this chart, in a cartoon-type way, is the driving influences basically the number of engines in the stage, the number of stages, and the ability to abort given an accident. Those are the things that influence the establishment of the loss of mission probability, and then the conversion from loss of mission probability to loss of crew probability. As I said, the loss of crew probability involves not only the accident, but the ability to abort given the accident environment. Next, please. Every step of the process, then, going from the ESAS to what we call the single stick, today what we call the Ares 1 vehicle, used a combination of the best tools available from both the probabilistic side, that is, scenario development using probabilistic risk assessment theory, and the physics side, that is, the best computational fluid dynamics simulations available using the best supercomputers available to establish the environment. And it's the confluence of the logical and the phenomenological that gave us the confidence that we have today that we were on the pathway to achieving that significant difference that Bo talked about in our crew launch vehicle. Next, please. Now, in a qualitative way, I show in this chart how one converts from loss of mission to loss of crew. Basically, with the various alternatives, you assess the accident conditions in groupings, which we call bins, each of which give us an implication of the particular accident environment imposed upon the crew module in three basic areas. One is fragmentation, one is in impulse, pressure wave progression, and lastly, in a radiant form from a thermal standpoint of the blast. And what you see here is an assessment qualitatively of the effectiveness of the abort system against those types of insults. And on the bottom, we show the probability of being in each one of those buckets or bins for each alternative. So it's the combination of those two things that produce what I'm going to show you on my last and final chart. Next, please. What you see here is the relative results of an independent assessment. Independent in the sense that the loss of mission calculations were done by our team, independent of anything that NASA or anybody else has done. And what we looked at was how much better would the Ares 1 vehicle be from a safety perspective, that is, from a loss of mission and loss of crew perspective, as compared to other launch vehicles. So here you see Ares 1 as the baseline, unity. And what we're speaking about is factors above in safety, above the baseline of the Ares 1, that the others would be worse. In other words, the worst risk, as Steve said. And you'll see that in every vehicle, across the line, at the mean, Ares 1 is at least a factor of 2 safer from a loss of crew perspective, and in some cases closer to a factor of 3. You'll also see, from a loss of mission perspective, the Shuttle C, since it is significantly based on the existing shuttle, is closer to the Ares 1 than any of the other alternatives. And it's the fact is that the conversion from loss of mission to loss of crew on the side mount, which makes the side mount as a factor of 3 worse from a loss of crew perspective. So there you have it. It's something that we've tried to do to address the goal that Bo talked about. Getting something not just a little bit better, but generationally better and safer from a crew standpoint. Thank you very much. I'd like to now introduce Alex.
Good morning. I'm Alex Priscus. I'm the first stage manager. It's truly a privilege to be here today. I want to communicate 3 basic thoughts to you that are simple, because I'm pretty simple, actually. The 3 thoughts that I hope to get across to you are a little bit in terms of the tasks that we've been asked to go accomplish and undertake. The way we chose to skin this cat, for lack of a better way to say it, because there are various ways to go about it. And then thirdly, where we stand in terms of progress. So go ahead and hit the next chart while I talk for a second. Let me talk about skinning the cat briefly, though. I'm a little bit different than some of the other folks that have had the privilege of working for NASA for a long time. I've been in the industry doing solid rocket motors and development on solid rocket motors and boosters for 25 years now, and doing the development piece continuously in that period. I've spanned from the commercial to the DoD, now to the human rated side of this. And in the way you go about it does vary. There are some fundamentals that are the same, but the way you choose to skin the cat does vary somewhat. And I want to talk to that here in a minute. But in terms of the task that we were asked, it really can be broken down into 2 simple things that we had to go do. We had to go take what is the best understood, most reliable large solid that this country has active today, which is the RSRM, and we had to adapt that to this architecture, this vehicle, its mission. That forced several design changes. It allowed us to keep many of the heritage pieces, but it did change it. It forced several fundamental changes also at the same time. In adapting it, though, we had one other task. And it really hits to what Joe was talking about and what Steve's talking about, and that other task was to make it better. What do I mean by make it better? In this one, the biggest context of make it better is make it safer. The nice part of making it safer on this one is we had a wealth of knowledge to work from. The fact that essentially after every mission on an RSRM, that thing gets a full autopsy. We not only know the strengths, but we know the weaknesses inside and outside of that vehicle. So in terms of making the mission and adapting this, the first thing we did was we went to a 5 segment to add more total impulse. But we didn't just stop there. Other than opening the throat up and changing the burn rate so that we could utilize the same case, we also took lessons learned from RSRM and lessons learned from Titan 4B SRMU to enhance the grain geometry. We added different radii, we added different features in that grain so that we could mitigate the risks of bore choking and other things that we have learned over the years. So there's a whole lot of knowledge that goes in to making this better and safer. I will mention a couple of other things that we specifically did as a result of our knowledge on RSRM, and that is we made some significant changes that we are trying to achieve relative to the nozzle. We actually are carrying two designs on the exit cone right now. One will be tested in DM1, another one will be tested in DM2. The purpose of that is to test out some objectives that will eliminate the consequence that we know of ply lifting or delamination that can sometimes occur. Although it's not critical, it's not good. The other thing that we have done is we've made some modifications to the TVC. This was a recognized issue on shuttle. As a matter of fact, this TVC system is shared between the booster and the orbiter. The orbiter made some improvements to the shaft seals on the fuel pump some time ago. The booster, for various reasons, was still in the process of making those when it was decided to bring the program to culmination, and so they didn't go ahead and adopt those changes. We have adopted those here. Notionally, what that has resulted in from a reliability sense, and you got to look at this thing relatively because these are probabilities, but it's about a 20% increased improvement of reliability on this booster is what is forecasted. We had a requirement of 1 in 1670 going into this program, and we believe we're a little better than 1 in 2130 right now. So those are some of the things that we did to actually customize or adapt this to the current mission. We've also added new electronics, new forward structures. As Bo mentioned earlier, I absolutely believe in some of his lessons learned in terms of robustness. And one of the places that our team took advantage of that was on the frustum. And it is a composite frustum. And you'd say, well, why the robustness there? Well, as it turns out, for the same mass properties and in about the same cost, we could increase our buckling margins by 40%. And with a new vehicle where you know loads are going to change, that turned out to be a critical place and one of the places where we tried to anticipate where we may need robustness, and we incorporated that. Next page. I'd like to talk a little bit about the uniqueness of this team because this team has had an opportunity to fully engage not only in the Ares 1 main vehicle program but also 1X. We are delivering the first stage for the 1X test flight that's coming up here at the end of October. The rail cars you see are the deliveries of the motors going down to Kennedy here last summer. On the left, you see a stage separation test that we enacted for 1X that had applicability. And one of the things I'd like to talk about is the interactions between the two programs, because sometimes that's underestimated. There are so many on that that separation test. We learned interactions between the parachutes in the pyro charges that are invaluable and will feed into the Ares 1 program. We have learned a lot going both ways back and forth in terms of thrust oscillation. You know, Ares 1 was ahead of the power curve in terms of thrust oscillations and understanding what it meant to primary structures. Interestingly enough, Ares 1X is actually learning more lessons about the 2L modes and what it means to secondary structures. And so there is so much learning going back and forth. Thirdly, the little movie that you see running here are the new parachutes that we're developing. We are developing those for Ares 1, but they will be used for their first time on Ares 1X. They are in the stack. They're ready to go. We've had a very, very successful development program and testing program on the chutes to date. Next chart. A little more in terms of where we are up in the top left-hand corner or our avionics boxes for first stage. We have 6 avionics boxes. All of the engineering units, prototypes are developed and are in testing right now. So we are significantly well on our way to maturing those and having them tested. I'll tell you, up on the top right is a photograph of one of the solutions that we've come up with to deal with the coupled dynamic response of thrust oscillation in this vehicle. And in 25 years, this is the first time I get a chance to really work this. We've seen the issues and solved it up at payloads on various vehicles different ways in the past, but this was truly a unique opportunity. You know, it's very similar to other development programs. As has been mentioned several times, there's not a real significant development program that you come into that you don't run into issues. That's just a standard part of this business. This is one of 3 solutions that we actually engineered, developed, prototyped, and have tested. This one's an isolation system shown on the top right. The other 2 are more thrust dampeners. Again, development will come with problems. This team, I believe, has very quickly responded and shown that they can formulate, fabricate, and test those solutions expeditiously. Lastly, right now, what you see on the bottom right-hand clip that is running is the assembly of DM1. DM1 is our first 5-segment full-scale motor test. You see it being put into the stand. There it is in the stand. We're less than 30 days out from that test. That motor is ready to go. It's ready to fire. We're in the final throes of putting instrumentation in it, and really excited to get the results. In the lower left is some tests that were done on the DM1 igniter. One of the reasons we wanted to retest the igniter is, like the motor, we have updated some of the subsystems in these. In both of these cases, we have removed asbestos from any of the insulation systems to make them safer and more environmentally friendly. So both the motor that we are testing and the igniter will be asbestos-free in this upcoming test. And then thirdly, on the next chart, please. There is DM1 in the test stand. We're ready to go. But furthermore, DM2 is right behind it. As a matter of fact, I mentioned we have 2 different nozzle designs. That nozzle for DM2 is already fabricated. It's ready to go. The motors, the cases are insulated, ready to go. I have held up casting only so that we can get the data from DM1 to make sure we don't want to make any alterations before we go on. But that's kind of where we are. DM1 is in the test stand. DM2 is chomping at the bit right behind it. I guess what I'd like to leave you with is the understanding of how far we are and the progress we've made, because when you think about these kind of major tests for those who've been around it, these are some of the biggest gates that we'll end up going through. There's still a lot of work in front of us, but these are some of the higher mountains that we'll have to climb. So with that, thank you, and I'd like to turn the time over to upper stage Danny Davis.
Thank you, Alex. How about those solids? First of all, just a pleasure to present our upper stage progress and status to the panel today. Robert showed you a engineering wheel that we are moving through. We are an in-house design activity at the Marshall Space Flight Center. We're supported by many other centers, the Glenn Research Center, Langley, and KSC. Also at Ames, we have some work. We are finalizing our design and manufacturing and operations baselines based on the learning we had at our PDR scrub, and we're heading right toward potting our information so that we can take this engineering and implement it. First slide, please. We have a very solid flow down of requirements, needs, objectives from the Constellation program, and our design is responsive to those. We have a safe design first. The performance is as it should be for the mission that we've been given. And we feel like our design will be affordable. Our design team we're actually doing 2 designs at one time. The design of the flight hardware, the configuration of the hardware, and the manufacturing system that goes with it. What this allows us to do is avoid any surprises in manufacturing that could be significant cost drivers later on. Our design is informed by a lot of heritage work that went on before us. Our structures are large aluminum lithium aerospace structures with friction stir welding. We have good experience with these processes. Now we've had to learn some new tricks so that we can, for instance, use friction stir welding throughout the design as opposed to just linear applications. We have, of course, a main propulsion system that provides loading and conditioning of propellants. And then we supply those propellants, liquid oxygen, liquid hydrogen, to the engine just as the engine prefers them. They're very picky about their propellants. We have a pressurization system that we've optimized to do that with as little risk as possible during the staging event. We went after those risks early on, and we feel like we've mitigated that risk. Our thrust vector control system is a hydraulic system driven by a turbo pump that's energized from gases off the engine. Very straightforward, very practical system for this application. The reaction control system has some heritage brought into it. Our roll control system has 600-pound thrusters on it, and that's a little bit of a challenge. It's a large thruster. But in this case and in all of our subsystems, any place we perceived a risk early on, we implemented advanced development programs, and we'll show you in a little bit that we've had great success in developing and firing these thrusters for our application. We have a composite interstage. We have a lot of flexibility there, as Alex mentioned, in the tailoring of the composite materials to our loads application. Our oldest selling motors, again, this is an in-house design of a small solid rocket motor, 4,000, 5,000 pounds, 4-second burn time. We've built these in advanced development programs and fired them and learned a lot from it. And you can see our baseball card there with our masses and all. Let me go to the next slide, please. This is where we discuss our avionics. We do in-house development of the avionics system, the architecture, the specifications for the components, and then the coding of the software. This has been a good challenge for us, and I think we've made great progress there. We're responsible for guidance, nav, and control, command and data handling, pre-flight checkout. We also do power distribution, instrumentation, all of the usual suspects in an avionics system. Our systems, our boxes and cabling are naturally distributed throughout the stage. We understand where all of these boxes go, what their functions are, and in what environments they have to be able to survive. Next slide, please. As I mentioned, the NASA design team has been working very closely with the production team so that we understand what the design needs to do to support production and the operation. The Boeing team has been on board with us from about 6 months before our PDR, and we have really enjoyed the collaboration there of merging production systems into the design flow. We've had hundreds of Kaizen events to lean out the manufacturing system, and that often pushes requirements back into the design world. We're very fortunate. Early on, we said we need manufacturing demonstrations. We were able to implement a very robust manufacturing development center here at the Marshall Space Flight Center, where we've worked on our robotic welding of friction stir welding of unusual shapes. In our case, we have elliptical domes that have to be welded together. This hasn't been done before, so we needed to go work that out. We had complex geometries in our common bulkhead. We had to go work that out. To date, we've had great success in this, and we've learned a lot. We anticipate that when we set up our production line at the MAF, the Machu Assembly Facility in New Orleans, that we will have the right tooling, we'll understand that tooling. As importantly, we'll have the right fixturing, the right processes, and the right skilled labor to walk into that job and be successful. One thing that the lab here at Marshall really provides us is if we're in production, on the production line, and we have issues, we've got a laboratory to go work those out, and that's very much important to us. You can see our friction stir welding, our large tooling, and the human intellect that's watching this, watching these developments. They're learning the hard way on some of these lessons, and it's our NASA design team and our Boeing team, shoulder to shoulder, developing these systems. Next slide, please. So we are invading MAF. The shuttle program has been able to clear a large section of the very large facility down there for us so that we can begin to put our tooling in. We're very mature with our large welding tools, some of our vertical tools, and we're ready to start installing those. One thing I'd like to mention also is the complex aerospace structures don't come easy. We have 18-foot diameter single forged Y rings and T rings, and that we've had developed. These have been delivered to us. We've investigated the processes required to make them, the properties you get out of that. Also, our bump form orthogrid panels. These components have been delivered to us. We've had a good look at how those the processes needed to make them, what we get out of that process, and then how we assemble those. We have 18-foot diameter single-piece spun-form domes that we're going to use in our common bulkhead. Very excited. It's a beautiful piece of hardware. I think some of you guys got to see it when you were down. Just excited to have that. Next slide, please. I mentioned that our design was informed by development testing. In the places where we perceived risk early on, we were lucky enough to get development components in place to go work. OLED settling motors, we've had successful firing. We're coming up on putting a more flight weight motor in a test stand so that we can validate all of the things we learned off the first firing. Reaction control and roll control thrusters have been tested with our partners out in Sacramento. The RCS team has also built a fluid mock-up so that we can look at water hammer effects, our propellants, and things like that. The thrust vector control team at the Glenn Research Center, we've done single-axis testing, and now we have our facilities almost complete so that we can start our two-axis testing up there. And I think that's my last slide. Next slide. With that, I would like to introduce a gentleman very important to the upper stage. It's the upper stage engine manager, Mike Kynard.
Thank you, Dan. I'm an engine guy, and from an engine guy's perspective, I always like to say thanks to Danny for that important review of the flight support equipment for the engine. So go to the next chart, please. Yeah, I wanted to talk a little bit today about the progress we're making on the development of the J2X engine. My team is very proud of the progress we've made thus far, and glad and pleased for the opportunity to come and share it with you today. We were given the task to build an engine that would meet the requirements of both the Ares 1 and 5 vehicles. It has a couple of different missions. For the Ares 1, it's the second stage engine, the upper stage engine, that will get us nearly to orbit, and then the Orion will do circularization from there. And for Ares 5, we're actually going to burn twice. We'll help the EDS perform the same mission to get to low Earth orbit, and then we will do the TLI burn to do translunar injection and progress towards the moon. We were asked to start with J2X, or excuse me, the J2 from the Apollo era, and that was based on the fact that the J2 had performed a very similar mission to this. And so we knew that we were starting from a good point, from a piece that worked. We needed to make some changes where necessary to be able to meet the Ares 1 and Ares 5 performance and vehicle requirements. And so we did that. We were asked to rely on heritage a lot, and a lot of folks think that just means J2 heritage. But really, the workforce we have was fresh off of developing the RS-68. We have a lot of history from the SSME program and from other rockets that Pratt & Whitney Rocketdyne has been developing over the last 30 years since the J2. And so we tried to take heritage where it made sense from several pieces. A gentleman at Pratt & Whitney Rocketdyne likes to say from a TRL level, a poker term, it takes nines to enter. And so we like to make sure that we have a good understanding, because we want to limit the amount of technology we need to put into this, so we can robustly get to an engine design that we can be ready to offer the vehicle for safe flight. One of the things we were able to do is make some changes to the turbo machinery that was based on the J2S design. We have been able to use the J2S pumps, and I'll talk a little later about those, to make some changes to help meet their performance and put some robustness into the system. Instead of using the original J2 gas generator, we actually, instead of scaling it up, we decided to scale the RS-68 one down. That was because the people at Pratt & Whitney Rocketdyne are very familiar with that design. For an engine controller, we're going very simply. We're going to go with an RS-68 based design and software architecture and make some changes for this to control this engine. We're going to use for the regen nozzle part, we're going to use a tube wall nozzle, and as folks that are maybe familiar with the SSB is concerned, they know that some tube wall nozzles can be complicated. We chose not to use a more complicated design. We were going to use a more simple design based on the RS-27. We took some other things from the from the J2, which was the flexible inlet ducts, the scissors ducts. That allows us to have a nice tight package for the upper stage. Allows neat solution for gimbling. Went with the hip-mounted main combustion chamber, which is a direct pull from the RS-68 program, which makes a much simpler manufacturing and much more robust manufacturing versus the structural plating done for the Space Shuttle main combustion chamber. And then the thing that gives us a lot of the performance we need is a big, large nozzle extension, and that we're going to make out of Haynes 230. We're going to spin form it, chemically mill it down to the right size, and it'll allow us to expand the gases and get a bit more performance. To our performance, we're roughly a 300,000-pound engine, 294,000 pounds of thrust at primary mode. We do have a secondary mode. We're able to throttle to a secondary position, and that will be used during the translunar injection burn. Our ISP is very aggressive with 448 seconds, but that's accomplished, and we think we've got a good way to get there by making injector changes that will increase the combustion efficiency, and also the large nozzle extension that allows us to gain performance through further expansion of the gases. Go to the next chart, please. We're making a lot of progress. We are past our critical design review on almost all pieces. We have a little bit left to go on the avionics. The avionics naturally lags to make sure it lines up with the vehicle very well. Well, as you can see, we have actually a lot of pieces that are getting put together for the first engine. We've got a good design. Those designs have gone out to the vendors. The vendors have begun to make the pieces, as you can see here. You can see turbine exhaust gas manifold forgings down the lower right-hand corner. The main combustion chamber spun liner, we're getting ready to slot that in just a few weeks. The turbo machinery for the first engines, the castings are here. We're beginning to make the disc and the shafts for those, and so we're making a lot of progress towards getting to our first engine firing. Go to the next chart, please. That design, the design that we have a lot of confidence in, was informed by some early testing that we were allowed to do. I mentioned before that we were able to take some of the turbo machinery and make a power pack and be able to put it on a test stand down at Stennis and actually run some tests with the Heritage J2 hardware at Ares 1 performance conditions. We could see what changes we needed to make to accomplish our mission versus the original J2. Down in the lower right-hand corner, we're also doing some subscale testing for the operation of the large altitude facility that we're building, the altitude test facility that we're building down at Stennis A3, and that facility is going to allow us to have long duration burn capability for simulating altitudes greater than 100,000 feet. And so we want to make sure that that the facility and engine come together at the same time, and we understand how to operate that facility. So we built subscale diffusers. We're running lots of tests there, and going to make sure that we can that we can robustly run that facility to support the test campaign. Next chart, please. Here's some more things we're doing. We built an early version of our gas generator. We brought it out here to Marshall and the East Test area. We tested it. We found some issues. We've made some design changes, and now we're back into testing again. In fact, we're testing this week on the workhorse gas generator. We think we have a good solution to some combustion issues that we had, and the testing this week should prove that out. Once we understand that, we'll go into making our combustion gas generators, our gas generators for the production engines. In the lower left-hand corner, you can see good progress being made on the altitude test stand A3. I was just there yesterday. It's an impressive size. They've got the barge docks in. The next thing to do is to start populating that big metal structure with the components for engine testing. And in the lower right-hand corner, you can see that we're actively engaging our vendors and our prime contractor in the development of the control systems, the valves, and the actuators. Next chart. And that's all for me. I'll turn it back over to Steve Cook.
So, Mr. Chairman, that wraps up the first hour session. What I'd like to do is open it up for any Q&A that you may have on this section. This afternoon, after lunch, we will be talking about our risks and our risk mitigation posture and what we've been doing there, as well as our flight test program, and then we'll give you a flavor for where we are on the Ares 5 concept. So, questions, please.
Well, thank you. That was a terrific set of briefings, and as I mentioned earlier, many of us have heard all or parts of those, so I don't know how many questions we have. Probably have some, though. Leroy, you have one.
Yes, I'd like to ask a question on the risk assessment. I think Joe Fragola.
Yes.
Yeah, could you put up that chart? You said it was your favorite chart, and I'm still struggling a little bit to understand it.
Okay. It's chart 3, including the title.
See, while they're finding it, first of all, I just wanted to ask a general question. Where did you get all your numbers?
Oh, okay. Those of one more. Ups. 1, 2, next one. Yeah. This is the chart you're referring to.
Correct.
Yeah. Okay. Each one of the abort effectiveness numbers were calculated just simply by determining what abort effectiveness you'd have to have in order to convert the failure per launch frequency to a safety number. And then I drew the ISO lines across to indicate that. The numbers for the various launch vehicles came from a combination of Isakowitz and updates of Isakowitz that we have. Also from the 45th Space Wing analysis, we have comprehensive data sets on each one of these launch vehicles, which I'd be pleased to share with you if you'd like.
Okay, I was just looking specifically at the Soyuz number 0.98. That seems, I think I've seen Soyuz numbers much higher than that.
Well, it depends upon you if you're talking about the recent Soyuz experience or across the spectrum of Soyuz launches. One of the things that someone mentioned here is maturity has a lot to do with your estimate. So if you're talking about Soyuz from now into the future, it's closer to 9.9, right? But it's about the same as the shuttle, as a matter of fact, in forecasted risk going forward.
Okay, well, nonetheless, I guess if I come down your Soyuz line and I assume a 95% effective abort system, I get to exactly to the target line, right?
Exactly right. But 95% effectiveness is a very difficult thing to achieve, and because we're talking about integrated abort effectiveness, and that is how effective your abort system is across the spectrum of abort scenarios at the various stages of the launch trajectory. So, one of the advances I think we've done in the Ares 1 development is to make use of supercomputer capabilities to quickly calculate at various points in the launch trajectory what the impact of different types of scenarios would have. So, for example, lower in the trajectory, blast propagation is important because you have atmospheric effects. Later on, when you lose those atmospheric effects for the same scenario, fragmentation takes over too. The combined impact of all of those, for example, in the Ares 1, is about an 85 to 86% integrated abort effectiveness. 95% is very, very, very difficult to get.
Okay, but I mean, in other briefings, we've been told that Ares 1 escape system is being designed to 0.95.
Okay. Escape is different than abort effectiveness. Escape is related to the probability if you push the button that the launch abort system works. What this talks about is, does it survive and remove you from the insult environment? It's not only the probability that the launch aborts. That's what I was trying to say. When you try to convert an expendable launch vehicle to a crew launch vehicle, it's not just whether or not the launch abort system works, and yet you have to do that. You have to design it to a high reliability, make sure it works when you press the button, but you also have to make sure when it works, will it allow you to survive the insult caused by the abort environment? One of the significant advantages, and one of the reasons why we're confident in the Ares 1, is that for a significant portion of the most probable abort scenarios on Ares 1, that is case breach or burn-throughs of soft goods, which represent historically over 80% of the solid rocket booster insults, those conditions are very benign from abort perspective. And it's the combination of the benign abort conditions imposed on the vehicle by the predominant failure modes with the already high reliability, demonstrated high reliability of the solid rocket booster. The combination of those two things, which makes us confident in Ares 1.
Okay, so those ISO numbers are not just the abort
That's correct.
hardware, it's the whole integrated system.
That's right.
In that case, where would Ares fall on these charts?
I said as I recall, it's about 0.8586.
Okay, do you have a pointer? Can you kind of show us where that might be?
It's about, this is 0.8, so 0.85 is approximately around in here. If you talk about a 1 in 200 or to 1 in 400 launch vehicle, you're talking about the Ares being up in this area, and that is rather significant. If you start looking at the probability that you'll get better than 1 in 1,000, no vehicle comes close to the Ares 1. And of course, models have uncertainties associated with it. That's why I showed the significantly large bands of uncertainty. But the fact of the matter is, it's the combined confidence of high reliability demonstrated on the SRBs for the shuttle with the understanding of the significant scenarios that create the abort environments that gives you that feeling of confidence on the Ares 1.
Okay, then help me a little bit, because we've been seeing numbers of Ares being 1 in 2,000, but you're saying it might even be a little bit less than 1 in 1,000.
Our calculations are better than 1 in 1,000. Better than 1 in 1,000.
Okay, then maybe I'm confused about what this 1 in 2,000 or 2153 number we've
Well, there are different, this was an independent assessment. There are different models, there are different teams. The teams haven't gotten together to resolve the uncertainties, but it's important to understand that independent of what the absolute number is, the thing to remember is the relative safety level of Ares 1 is significantly better, to talk about both, significantly better than all the alternatives and significantly better than the current shuttle. Even though the shuttle has demonstrated a very high level of reliability, it's a question of reliability and abort effectiveness that makes the combination.
Okay, thank you.
If I might, I've got a question on the same topic. Does anyone else have the same topic? You do. Go ahead, Jeff.
There's something that I think we've come to understand as we've heard a lot of fact-finding briefings, but I want to get on the record because people who are listening to these briefings may not have been through all of that process, which is you really have to be careful about comparing the probabilistic risk assessment of an as-yet unflown vehicle to the demonstrated reliability of flown vehicles. Probabilistic risk assessments look at hardware-driven random failures, and then you have a very sophisticated methodology in which you do your very best to look at what that effect is on the system failure. But in round terms, historically, about 10% of the failures of launch vehicles are driven by those kinds of random effects. So not only do PRAs grossly overstate the reliability of an as-yet unflown system, a fact everybody is aware of, but it also means that you got to be really careful driving your program design with, factors of 50% or factors of 2 on probabilistic risk assessments, because at the end of the day, you don't really know what the real reliability of the launcher is within a factor of 10. So there's nothing wrong with using PRA to guide your decisions, but you've got to use the numbers with great caution.
I think that is a very important point, and it's one of the strengths of the Ares 1, because the demonstrated reliability of the SRB is solid, and in more ways than one. And all the other vehicles also require a second stage. So the second stage, to a degree, is not a discriminator on safety, because all the vehicles require a new second stage. The first stage of all the vehicle alternatives, with the exception of the Shuttle C, the demonstrated reliability and the demonstrated risk is much, much better for the Ares 1. From that perspective, the Ares 1 is far superior from all the other alternatives. If you look at the Delta IV Heavy, for example, we've only had 9 Delta IV launches and only, 2 Heavy launches. And in the first launch, there was a discrepancy. Okay? So from precisely the perspective you're speaking, that's one of the strengths of the Ares 1.
Let me add that your history you're taking a big risk by assuming in that statement that future new launch vehicles, however derived, will not also experience early anomalies, because that is the history of launch vehicle development.
Absolutely. If you look, it would take me a long time to go through the whole thing, but yes, absolutely. Where you look in the history of a launch vehicle is very important. How many test flights you have is very important. The growth history of any launch vehicle is significant, as any other developmental system, and that has to be taken into account. When we looked at these numbers here, these are numbers that, in my comparative chart, were numbers taken at the mature level of all the launch vehicles, at the first lunar flight, we called it. So in other words, we anticipated successes on the Delta IV Heavy until 2015, and still the Ares 1 forecast is 2 times better. And it's precisely because of the failure modes interacting with the abort effectiveness. Yes, sir.
Yeah, if I may, I'd like to weigh in on this too. Jeff said much of what I wanted to say, but my own experience has been with calculated reliabilities has been not very happy. The one thing I've learned is the calculated numbers are always higher than the real world numbers, almost invariably. Over the years, I've kind of drawn the conclusion that the expendables are somewhere like 96% moving to 97. Shuttle was like 98 moving to 99. The astronaut office said, I think they wanted 3 nines at 95% confidence. And even if we use the calculated numbers, you've got, we don't get to that level by a considerable factor. And it's likely the real numbers are going to be well under the calculated numbers. And having said that, Jeff, I would take one small issue, semantic, I suppose, with what you said, that one of the things I've learned is that there's no such thing as a random failure, that there's a reason for every failure.
I think that's one of the reasons why we wanted to do a comparative assessment rather than an absolute assessment, for the very reason that you mentioned, and why we tried to focus on the historical demonstrated statistics rather than on forecasted bottom-up numbers.
Les, you had a question.
Yeah, a question to Alex, but before I do that, Steve, I'd like to compliment you and thank you for answering my acquisition management questions. My questions were not pejorative ones or critical ones, but they were also shaped by DoD lessons learned, as you noted on your chart, where we've gone the spectrum from LSI, lead system integrator, to the government being the total integrator, if you will, and have had problems on both sides. And it was the latter that we heard some comments, if you will, from some of the contractors, but they also said that the communication now is much, much improved, and they recognize that it was sort of the early lesson learned of going through the different changes in roles. So compliments to you and the way you and your team are doing this. I'm very, very impressed with the way you've tried to approach it.
Thank you, sir.
Okay. My question to Alex deals with the thrust oscillation mitigation approaches. You've mentioned two, the isolation versus thrust dampeners, and I don't know if you've settled on any one of the 2 different schemes, and more importantly, are there design impacts or performance impacts on either that would weigh into your decision?
First of all, General, let me say the solution needs to be a system solution, and it is being looked at by Level 2, and they are making the decisions, and I'll tell you what the current baseline here is in a second. But when we identified this issue from a first stage perspective, we went and looked at the two physical ways to mitigate this, and one was to isolate it, and two was to absorb the energy somewhere else. And so we actually designed, other than what you saw, which was the isolation system, we designed and have tested two dampening systems, which people simplistically call them a mass on a spring kind of thing. One's active that actually cancels, like your Bose headphones that cancel out noise in an airplane, and the other one's passive. Both of those are actually sitting on the shelf because as we did the system analysis in looking at different ways to do this at the system level, we were looking for the simplest way to get the effective solution. And that simplest way right now, the program has determined are two isolation systems, one between the first stage and the upper stage, and one between the upper stage and Orion. Steve, do you want to add any more?
So what we're doing there, General, is we're carrying, and John Hutt will talk about this a little bit this afternoon, we're carrying some risk mitigation on that. One, because one of the solutions that we've been carrying along is coming up the technology readiness level curve very, very fast, and that's what we call the lock stamper. And the elegance of that is it uses something that's in situ to solve the problem. It uses the mass of the locks, capture about 30% of the mass, put it to work. It just pounds this problem flat. And gives you a very wide range where frequencies could move and things could change, so it increased our robustness. So we've been hustling it along such that later in the summer, early fall, we will take a review point and say, do we want to stay on this baseline that we're off mitigating to, or is there more benefit to going to a dampening system like the lock stamper? Things like the active mitigation, we've really kind of put on the shelf as a very, very remote backup, but we've got it if we need it. That's the noise canceling headphones approach that Alex talked about. That answer your question?
Yeah, I think the LOX dampener is that unique system you showed us during our last visit here.
Correct,
And
exactly.
Very impressive. Thank you.
I think we have time for one more question, and Bo, you had that.
Yeah, my question is to Joe Fregola. Joe, you know, when I worked on a system built by Soviets or Russians later, I always had a sense that they were less relying on fault tolerance and more on good design, good engineering, and then test the heck out of it, you know. And the question specifically it has to do with number of parachutes. We have 3 parachutes where 2 out of 3 is sufficient to get you safely to ground on Orion. Soyuz use single parachute with a single backup. Have you done any analysis and shows which part of the world is right?
You know, that's a very interesting question. We had extensive work, not for this study, by the way, extensive work on that alternative, and it's you know, not clear. It depends a lot on the mass of the vehicle. All right, because there's a limit to the size of a single chute mass, at least in terms of it, as I understand it, at least in terms of reliable deployment of the chute. Soyuz is a lot lighter than the Ares 1, and so I believe, and it's been some time, and I'd have to look it up, I believe that one of the problems was that we couldn't get a single chute that was big enough to handle the load reliably with enough margin, and therefore we had to have at least 2 chutes, which gives you the 3-chute system, unless you're going to launch two chute systems, and then you have the problems of potential entanglement and things like that. And I think that the trade came out, the 3-chute system was best for the mass that we had.
So am I hearing you to say that if you could build a big enough chute single with a single backup would be more reliable?
I'm saying that it's a significant trade, and the trade is not clear. It depends upon how, it depends upon, first of all, for example, the common cause failure effects and the interactive effects. It's not a simple calculation. It depends upon what you assume on that. There's not a lot of information related to common cause failures of single chutes versus multiple failures of double chutes. So I think the trade has been done from the perspective of the existing systems, and in that case, the 3-chute system came out the best. But if there were bigger chutes that were demonstrated, that might change the equation.
Okay, let me, on behalf of my colleagues, thank each of you for your presentations. We'll look forward to the rest of the discussion this afternoon. I picked up one open item, which was, I think, Jeff, you'd indicated that there were differences in your view with those of aerospace in some areas of schedule and cost. And could we ask that you get together with aerospace, not with the idea that you'll come to an agreement necessarily, although that would be nice, but that you could give us an understanding of where it is you disagree, what drives the disagreement. And if you wouldn't mind doing that, we'd appreciate it. Got it. Yeah.
Just very briefly, another action item is there's got to be a huge amount of backup data behind these charts. And in my copious spare time, I'd like to read some of it. I wonder if we could get that as a data dump.